Introduction of the S12XE 16-bit Automotive Microcontrollers, Freescale Corporation. Welcome to this training module on Freescale's S12XE 16-bit Automotive Microcontrollers. This training module provides an overview of the S12XE family microcontrollers and their internal functional circuits. S12XE family of microcontrollers featuring the XGATE coprocessor combines 32-bit level performance with all the existing advantages of 16-bit architecture such as cost effectiveness, code size efficiency, and excellent electromagnetic compatibility. The XGATE coprocessor enables it to more efficiently handle interrupt events and execute non-critical applets. There is a high-level compatibility between the S12XE and the S12XD families. The S12XS family provides an economical, compatible extension to the S12XE family. The S12XE has larger memory options, error correction code, enhanced EEPROM functionality, and an advanced memory protection unit as standard. These advanced features help simplify product development, increase flexibility, and reduce overall system costs for automotive body and multiplexing applications. The S12XE family features an enhanced version of the performance-boosting XGATE coprocessor, which has improved interrupt handling capability and is fully compatible with existing XGATE modules. The S12XE family also features an enhanced MSCAN module which, when used in conjunction with XGATE, delivers full CAN performance with virtually unlimited number of mailboxes and retains backward compatibility with the MSCAN module featured on existing S12 products. In addition, the S12XE family is composed of standard on-chip peripherals including up to 64 kilobytes of RAM, 8 asynchronous serial communications interfaces, 3 serial peripheral interfaces, an 8-channel enhanced capture timer, 2 16-channel timers, a 12-bit analog-to-digital converter, an 8-channel PWM, 2 I2C blocks, an 8-channel 24-bit periodic interrupt timer, and an 8-channel 16-bit standard timer module. Here shows a view of all S12XE family members, their flash memory capacities, RAM, EEPROM, and peripherals. The CPU-12X is a high-speed 16-bit processing CPU. The CPU-12X instruction set is a proper superset of the M68HC11 instruction set. The CPU-12X retains all of the instruction sets of the original CPU-12. The only exception that requires consideration is that the interrupt stack frame on the CPU-12X is increased by 1 byte due to the extended condition control register. Dedicated address generation logic and pipelined execution improves the CPU-12X performance relative to the CPU-12 architecture. The XGATE module is a peripheral coprocessor that allows autonomous data transfers between the microcontroller's peripherals and internal memories. It has a built-in RISC core that is able to pre-process the transferred data and perform complex communications protocols. The XGATE is a 16-bit RISC processor core running up to double the S12XE CPU bus speed. Its RISC core is able to pre-process the transferred data and perform complex communications protocols. The XGATE module is intended to increase the microcontroller's data throughput by lowering the S12X CPU's interrupt load. The XGATE can deal with lots of different kinds of events in a system, but is especially good at dealing with messages from other systems. It can take each of the LIN events and only alert the CPU when a whole valid message has arrived. The XGATE can also detect when a LIN message is not for the system and either ignore it or resend it on another bus. Here are the external bus interface signals that are used by the S12XE devices. Two operations can be performed on the external bus, read and write. During a write operation, data is transferred from the S12XE microcontroller to the peripheral connected to the external bus. During a read, data is transferred in the opposite direction, that is, from the peripheral to the S12XE microcontroller. The address lines are always driven by the external bus interface even when there is no external bus access performed. The clock generator creates the clocks used by the microcontroller. The individual clocks are gated by conditions of different modes, such as stop and wait, and by setting respective configuration bits. The peripheral modules use bus clock. Some peripheral modules also use oscillator clock. The clock monitor performs a course check on the incoming clock signal. The clock quality checker more accurately checks the clocks in addition to the clock monitor. The COP watchdog enables the developer to force a reset if not served properly. The real-time interrupt can be used to generate a hardware interrupt at a fixed periodic rate. Reset is an active low bidirectional reset pin. As an input, it initializes the microcontroller asynchronously to a known startup state. As an open drain output, it indicates that the system reset, which is internal to the microcontroller, has been triggered. The period interrupt timer is an array of 24-bit timers that can be used to trigger peripheral modules or raise periodic interrupts. The main parts of the PIT are status, control, and data registers, 2 8-bit down counters, 8 16-bit down counters, and an interrupt trigger interface. The 24-bit timers are built in a two-stage architecture with 8 16-bit modulus down counters and 2 8-bit modulus down counters. The PIT module contains 8 hardware trigger signal lines, PIT trig 7 through 0, 1 for each timer channel. Each timeout event can be used to trigger an interrupt service request. For each timer channel, an individual bit in the PIT interrupt enable register exists to enable this feature. The analog-to-digital converter is a 16-channel, 12-bit, multiplexed input, successive approximation analog-to-digital converter. It is structured into analog and digital subblocks. The analog subblock contains all analog electronics required to perform a single conversion. Separate power supplies, VDDA and VSSA, allow isolation of noise from other microcontroller circuitry from the analog subblock. The sample and hold machine accepts analog inputs from the external world and stores them as capacitor charge on a storage node. The analog input multiplexer connects one of the 12 external analog input channels to the sample and hold machine. The external trigger feature allows the user to synchronize ATD conversions to external environment events rather than relying on software to signal the ATD module when ATD conversions are to take place. The I2C bus is a 2-wire bidirectional serial bus that provides a simple, efficient method of data exchange between devices. Being a 2-wire device, the I2C bus minimizes the need for large numbers of connections between devices and eliminates the need for an external address decoder. It has two signals, IIC SCL, the serial clock line, and IIC SDA, the serial data line. IIC SCL is the bidirectional serial clock line of the module. compatible with the I2C bus specification. IIC SDA is the bidirectional serial data line of the module, compatible to the I2C bus specification. This module is a communications controller implementing the CAN 2.0A or B protocols. It has 5 receive buffers with a FIFO storage scheme. A flexible maskable identifier filter is provided to support 2 full-size extended identifier filters or 4 16-bit filters or 8 8-bit filters. The MSCAN module adds a new manual control for recovery from bus-off conditions. In the manual mode, the bus-off recovery is under software control after 128 times 11 received bits. The PWM module has 8 channels with independent control of left and center aligned outputs on each channel. Each of the 8 channels has a programmable period and duty cycle as well as a dedicated counter. The flexible clock select scheme allows a total of 4 different clock sources to be used with the counters. Each of the modulators can create independent continuous waveforms with software selectable duty cycle rates from 0 to 100%. The PWM outputs can be programmed as left-aligned outputs or center-aligned outputs. The serial communications interface features new hardware support for the following: ERDA protocol, LIN detection of brake signal and bus signal collisions, wake-up interrupts on active edges, and alternate pin polarity on the receive and transmit pins. The SPI module allows a duplex synchronous serial communications between the microcontroller and peripheral devices. Software can pull the SPI status flags, or the SPI operation can be interrupt-driven. It supports 16-bit data transfers as well as 8-bit transfers. This is controlled via a new transfer word in a control register. The basic timer consists of a 16-bit software programmable counter driven by an enhanced programmable prescaler. This timer can be used for many purposes, including input waveform measurements while simultaneously generating an output waveform. Pulse widths can vary from microseconds to milliseconds. This timer contains 8 complete input capture, output compare channels, and 1 pulse accumulator. The input capture function is used to detect a selected transition edge and record the time. The output compare functions are used for generating output signals or for timer software delays. VREG 3V3 is a tri-output voltage regulator that provides 2 separate 1.84 volt supplies differing in the amount of current that each can supply, and a 2.82 volt supply. The regulator input voltage range is from 3.3 volts up to 5 volts. It has 3 parallel linear voltage regulators with a band gap reference, low voltage detect with low voltage interrupt, power on reset, low voltage reset, high temperature detect with high temperature interrupt. The interrupt controller module for the S12XE allows up to 7 levels of interrupts to be available to the user. The XIRQ, SWI, BDM, unimplemented opcode, and system reset interrupts are available. Each interrupt source can be allocated one of 7 possible interrupt levels. New interrupt vectors include one for detection of spurious interrupts, like where an interrupt source is removed before the vector is fetched, one for the new sys instruction, one for CPU, MPU violations, and one for XGATE microprocessor unit violations or software errors. The S12XE family of microcontrollers support similar tools and third-party developers, as well as Freescale S12X products, offering a widespread, established network of tools and software vendors. In this example, the MC9S12XE is implementing the features of a typical car body controller application. The module interfaces with the main CAN buses distributed in the car using the on-chip MSCAN module, whereas the LIN bus communicates with functions local to the body controller. In both cases, the communications functions are managed by the XGATE independently of the CPU. The MC9S12XE provides direct control of power drivers for lights and pumps and reading of sensors using the on-chip PWM and ATD modules. Finally, the SPI interface to the RF receiver provides the interface to the car remote access system. In this application, the MC9S12XE provides gateway functionality between its on-chip RAM and LIN modules. Much of the low-level communications functionality is handled by the XGATE, which frees the CPU to manage higher-level communications and other direct connections to the module.